Hello and welcome back to Semiconductor and Thermal Management series. Today we're diving into the world of emerging thermal management materials. We're going to explore new compounds, composites, and technologies designed to manage heat more effectively in semiconductor packaging. From graphene-based TIMs or even ceramic metal hybrids, these materials are redefining what is possible in power density, heat transition, and thermal stability. Let's get started. This video is structured to walk you through the material landscape, starting with why material selection is critical in thermal management. We will then explore advanced thermal interface material, high conductive substrates, carbon-based materials, and emerging nano material. We will also be covering phase change material, metal matrix, and ceramic-based material, including liquid metal alloy. Lastly, we will go through two case studies which will demonstrate how these materials are being applied in real-world semiconductor systems. Finally, we will also look at future trends, which will include self-regulating material and integrating cooling structures that will make the longevity of a semiconductor much longer. As the technologies are developing behind thermal management, the goal is also changing. The desire of higher power increase and package size decreasing, the role of thermal management material has become more complex. In these images, we can see a cross-section of a semiconductor packaging, which shows the material, including the thermal interface material, known as TIMs, metal matrix composition, or MMCs, and high conductivity substrate. These materials must handle intense heat loads while also maintaining the mechanical integrity along with the electrical insulation and the capability of surrounding structures. The goal is not only to conduct heat efficiently, but manage heat dynamically, ensuring that each layer of this packaging contributes to the thermal dissipation. In semiconductor packaging, the choice of material directly impacts the thermal resistance, electrical isolation, and mechanical stability. In thermal conductivity, the material matters as each offer unique composition, for example, copper, aluminum nitride, and graphite. On the first image, you can see a perfectly defined semiconductor packaging. On the second image, you can see a packaging with thermal cracking, a clear indication of mismatched thermal expansion. Engineers must balance thermal performance against factors like cost manufacture and how long-term reliability as a power density increases. The role of advanced thermal material becomes even more critical. Now, let's dive into the properties that actually defines thermal management material. Thermal conductivity, that determines how effectively a material can transfer heat. CTE, also known as the coefficient of thermal expansion, is how much of a material can expand or contract under thermal or temperature changes or pressure. Dielectric strength, which is essential for maintaining electrical insulation while conducting heat. And lastly, thermal ability, which is the resistance to degradation under high temperature cycling. Understanding these parameters allows engineers to select the right material for each thermal interface with a packaging. In the picture, you can see the composition that matters when choosing a material, and environmental conditions are also included. TIMs, are also known as thermal interface materials, fill out the microscopic gaps between the surface, enhancing the thermal contact between components. In the first image, we can see a graphene-based thermal paste being applied to a power diode. Graphene TIMs offer ultra-high thermal conductivity with a minimal thickness, making them ideal for compact devices. In the second image, we can see a carbon area used as a thermal interface layer, which is more flexible in advanced solution that combines conductivity and flexibility. New emerging TIMs aim to reduce contact resistance, proven pump out and withstand thermal cycling without any degradation. Now let's talk about high conductivity substrates and boards. In high power modulus, substrates must combine electrical insulation and thermal conductivity to effectively spread heat. The substrate shown here is a common choice for power modules, offering the conductivity in 180 to 200 watt per meter kilowatt range. On the right, we can see a PCB with a copper inlay and hybrid approach. That's a copper directly into a board, creating thermal pathway, while also maintaining a structural integrity. The substrate formed the foundation of thermal management, connecting dial-level heat sources to a system-level cooling. Phase change material, also known as PCMs, absorb and release heat by changing phases. It typically changes from solid to liquid and back to solid. In the first image, we can see a PCM module integrated into a power package, which is designed to absorb heat during power surges. And on the right, the temperature stabilization curve shown how PCM's activation smooths out the temperature spikes, protecting the sensitive components. PCMs are particularly effective in applications with periodic high power loads, such as our power amplifier or high-frequency switches. The most popular PCMs also include paraffin, wax, salt hydrates, and more advanced technologies. Carbon-based materials, including graphite, graphite, and CNTs, which are known as carbon nanotubes, provide some of the highest conductivity available. The graphene heat spreader in the first image is placed directly over a power die, which allows rapid lateral heat transfer. In the second image, the carbon tubes form a flexible thermal path ideal for a compact or regular shaped packaging. This material is not only conductive heat effectively, but also reduces weight and maintains electrical isolation, which is critical for RFs and power electronics. Metal matrix composition, also known as MMCs, are basically combined material like copper and aluminum with a ceramic particle or carbon fibers, creating a material which has customizable thermal properties. The copper graphite MMC, which is shown here on the right, has thermal conductivity with a reduced weight, which is a common choice for power electronics. And on the right, we can see aluminum silicon carbide, are also known as ALSICs, with a substrate designed to manage thermal expansion, while also maintaining a structural integrity. MMCs are ideal for mission-critical application and balancing thermal performances with mechanical strength. Ceramic and ceramic-based materials, including aluminum nitrate, silicon carbide, and boron nitrate, offer a thermal conductivity while maintaining electrical insulation. In the first image, an aluminum nitrate ceramic substrate dissipates heat and a powerful module. On the right, a silicon carbide heat sink showcases the structural strength and thermal efficiency, which can make an ideal high-power transistor and our amplifiers. Ceramics are increasingly used in hybrid systems, combining mechanical toughness with thermal stability. Liquid metal alloys, gallium-based alloys mostly, can offer some of the highest thermal conductivity available, but it comes with its unique challenges. In the first image, we can see a liquid metal applied to a power module. This creates a low-resistance thermal path. On the second image, it's a microchannel cooling system which utilizes liquid metal, demonstrating how it can navigate tight spaces while also maintaining rapid heat transfer. However, issues like oxidization and leakage must be managed carefully in a liquid metal system. For these reasons, they are known to be having a high maintenance or more challenges. Encapsulation can protect components from environmental stress while also maintaining thermal transfer. Here on the left is a proximate mode. Compound is applied over a power die, forming a protective wall barrier. And then on the right, there is a ceramic field encapsulation material enhancing the thermal conductivity without compromising the electrical insulation, which is essential for ICS and RF modules. Newer formulations are being developed with more ceramic fillers and nanoparticles, which will enhance the thermal material composition. Thermal adhesives can bond components while also conducting heat efficiently. On the first image to the left, we can see thermal adhesive applied between a die and a heat sink, which is typically how the structure is made. And then on the right, we can see a nano filler and a thermal adhesive which can provide both conductivity and flexibility, which is critical balance for a high stress and high power application. Now, we can apply all this knowledge into different case studies. The first case study is based on graphene TIMS power modules. In this application, the power module is to reduce junction to case resistance. You can see it on the first image where you can see heatsink, TIM, and heater packaging substrate. The graphite paste reduces the temperature 15 degrees Celsius under continuous load. This can enhance the conductivity without compromising any electrical insulation or mechanical damage. Now, on case study 2, we go through a ceramic metal hybrid substrate. Over here, it's used with aluminum nitrate substrate with a copper inlay, which can also improve the thermal cycling by 20% over aluminum. This is targeted on high power RF amplifiers and power converters. As you can see on the picture B, how the heat sinks and heater fluctuates with different TIM. In this video, we have studied different materials and different ways the material can affect a thermal packaging and their challenges. In the future of thermal management lies on smart materials along with carbon structures and integrated cooling pads. As the power density considered materials like graphene, MMCs, and liquid metals will play a key role in maintaining performances and reliability. Expect to see future imaginations of thermal pathways and the substrate level along with material that can adapt dynamically to a powerful infrastructure. Thank you for watching. Hope you had a better understanding of why materials matter in thermal management and the new emerging technologies coming with PCMs, MMCs, and different liquid alloys that will change the thermal packaging technologies in the future.